Okay, now I hit the button. Thanks for reminding me. Okay, so it's a one-weighted undirected graph. So, sorry, weighted undirected graph. This is important. Undirected. So if it's directed, there is actually a concept called spanning tree and minimum spanning tree, but the algorithm is a lot more complicated. And at least for programming contests, I don't think I have seen the directed version at all. So anyway, undirected graph. It's weighted. So you have G, which is the set of vertices and also the set of edges. You want to choose a subset of edges such that what A, the graph is connected with these edges, with this subset. And B, the sum of the edge weights chosen, it's minimized. Okay, so those are the definitions of minimum spanning tree. And I guess that's with many of these problems, you can say maybe you only care about the weight, the total weight of the spanning tree, or maybe you actually care about not just the weight itself, but actually the set of edges that you chose. Right? So it turns out that it doesn't really cost you that much more to compute both of these. For some problems, sometimes it's easier to find the optimal value instead of getting the actual solution. Okay, so this is the idea, and there are a few things that I guess, why is it called spanning? Well, spanning just means that between any node, you can go from one node to any other node. So it covers the whole graph. And why is it called tree? So imagine that if you have a graph and you have some edges and you decide that these are the best edges. Okay, perhaps I should also say generally the weights are usually non-negative. Perhaps in most problems it's actually strictly positive. So if you decided that this is the subset of edges you choose and maybe there are other edges that you don't choose, well, if there's a cycle here, you can always get rid of one of the edges. Okay, so if there's a cycle here, you can always get rid of the heaviest edge and still have everything connected. Okay, and that's why, and so basically what it means is that you don't, in the subset of edges that you choose, you should never have a cycle. Okay, and if there's no cycle, then it's what we call a tree. So a graph with no cycle is a tree. So the result is always a tree. And of course, minimum, it's self-explanatory. Okay, so that's the setup. And I guess maybe I'll ask you guys in 3620, how many minimum spanning tree algorithms did you talk about and which ones?
I know we talked about prims and Kruskal's. I don't
Okay.
remember if we talked about any other ones.
Okay, good, good. Those are the two standard ones that I was hoping everybody knows. So anyway, you heard of it. Hopefully you know, but I'll do a very quick review. And so Kruskal's is actually the one that I personally use most of the time because it's the easiest one, I think, to implement. So how is this Kruskal's algorithm working? So Kruskal's algorithm says, take all the edges and sort by increasing weights. So we look at the lightest edge first, and then the next lightest edge, and so on. For each edge, E equals to UV. Ask, so do what? If U and V are not already connected, So it's not already connected. So we're not talking about connected directly by edges so far, edges so far. So for example, you could have, maybe you took these two edges and now you have this edge that you're considering, then this edge, it's already connect two things that are already connected. So then you don't consider it. So you only consider something, you only consider an edge if it doesn't connect something that's already connected. Okay, because if it's already connected and you try to add this edge, you're going to create a cycle. So let me go back to writing my pseudocode. So if U and V are not already connected, then choose this edge. And that's it. That's the algorithm. Okay. So this part, it's you sort the edge weights. So there are m edges. So that's m log m is the complexity for sorting. And then this loop, of course, it's m edges. So this loop runs m times. And then you have to keep asking if two things are connected. And the question is, how do you keep track of what is connected or what is not connected? So what is the answer for you guys that in 3620? Do you remember? What is the answer to figure out whether two things are already connected by the edges chosen so far? Do you know? Did you talk about that?
Union find?
Yeah, the two names for it, they're the same thing. Union find data structure, or sometimes some people call it disjoint set data structure. So I'm not going to go through how these works, but basically it allows you to very quickly say two things are connected. And then you can also very quickly ask if two things are connected directly or indirectly through previously connected things. And I will kind of say this is not correct, but I put quotation mark because it's not really correct, but it's almost constant time. I don't know, did you guys ever talk about what is the complexity of union find? Or is it something that's probably too advanced for 3620?
Yeah, I don't remember talking about that.
Okay, yeah, it's likely that it's too advanced to fully describe in 3620. So all I'm going to say, and maybe that's all the book says anyway, is that it is almost constant time. Okay, just pretend it's constant time. So in any case, what that means is that this first step takes m log m time, and then this loop run it m times, each time is constant time. So it's basically big O of m complexity. So altogether, it's m log m complexity. Okay, so whole algorithm, it's m log m. And it's really, I would say, easy to implement. And in fact, if you go to my code library, so if I go to the code library, there's some code called MST, minimum spanning tree. And this is on GitHub. You see there's union find, my implementation of union find. And then Krusko's algorithm is basically here. Okay, you sort the list. And then for each edge, you loop through the edge. You basically check if the two vertices that are in the edge, are they connected? And you use the union find to see if they have the same label. And if they have the same label, then they are connected. Otherwise, they're not. And then you choose it. You add it to the total sum of the weights that you selected, and then you converge to let union find know that these two are now connected, and therefore all the indirectly connected things are also connected. Okay, so that's the Krusko's algorithm. And I would say that in my programming contest experience, 99% of the time when I solve a minimum spanning tree problem is to use this algorithm. But sometimes I have to use the other algorithm. So what's the other algorithm? Hang on, where am I? Oh, I am here. Okay, so what's the other algorithm? Is Prim's algorithm. And Prim's algorithm, it's a little bit different. So Prim's algorithm, it says you start somewhere, start anywhere. Okay, start at a vertex V. Okay, then you throw all neighbors W. Well, okay, maybe I should, hang on, I shouldn't use W because W is the weight. So UV, okay, let's say U. Throw all neighbors U of V into a priority queue. Okay, into a priority queue where the priority queue is the one that keeps track of the minimum. And each neighbor, it's going to go into this priority queue with the weight of the edge V to U. Okay, so basically you're going to throw in all the neighbors and you're going to also throw in the weight of that edge that gets you from V to U. And then you basically have this kind of loop that says, well, the priority queue is not empty. Then take, let's call it, what would I want to call it? V equals to the front of the priority queue and pop priority queue. And then the edge that, so if V is already visited, then you just ignore it and continue. So I guess ignore, continue. Otherwise, the edge was chosen. So I guess if you have to remember when you choose V, you have to, when you put V into the priority queue, you actually have to know that who was the parent that put you into the priority queues. Otherwise, you don't know where you came from in the edge. So this algorithm is a little bit longer to write, so I got to erase this. And then, sort of for each neighbor U of V, you basically do the same thing as before. You throw U into the priority queue with the weight of the edge. So what happened is that you start off from somewhere. So you start from somewhere. Then you have a bunch of neighbors that you added to the priority queue. Those are the ones that you can reach. And then maybe they have some weight. And because this is a minimum priority queue, you will always pick the one that has the smallest one. So you pick this one. And then now that you pick this one, you add all these other neighbors too. But some of this, for example, here, you could have a neighbor that's already added, but maybe you add it with a different weight. Okay, so maybe you have something like this. Let's make 8. And then the next one that you choose is it's the one that has the smallest edge, so it'll be this one. Okay, and then you add all the neighbors. So maybe there's another edge. Maybe there's only one edge going this way, and it's 1. Okay. Well, in this case, even though this is short, oh wait. Okay, this would not happen because I would have already added the edge from this way. Okay, hang on. So that this is so let's say this is another 3. Okay, so when you see 3 here, you pick this one because maybe when you have a tie, you just pick either one. So now you see the next one is this edge, but this edge already connects you to something that has already been chosen, visited. It's already connected. So you just ignore that edge. And then you take the 4 and you add the neighbors, you take this 4, etc., etc. Okay, so basically you have this priority queue that keeps track of the cheapest way, of any way to reach to a vertex based on the edges that you have examined so far. And then you always pick the cheapest available edge that you haven't considered yet. And if it managed to connect you to something that you haven't seen before, you choose it. If you connect something to something that you already seen before, then you don't choose it because it's already connected, so you'll create a cycle. And that's pretty much it. You have to be a little bit careful, I guess, that when you throw things in, you don't throw things in if it's already visited. So here, so for example, if U is already visited, then don't, well, okay, so I guess this is not really the right way to say. If not U is visited, then do something, then do this next part. Okay, because if U is already visited and you throw that U in anyway, then at this time, when you pick it out, when you eventually pick it out, you just ignore it anyway. So you're basically wasting your time. And if you do that, then you can make your code a little bit faster. But anyway, the complexity of this algorithm is, do you talk about this? I'm sure you talk about this. It's really the fact that priority queue is basically logarithmic time, and it's roughly this much. Well, log n and log m are the same because n and m are, well, m is basically n squared in the worst case. So log n and log m are essentially the same. Okay, so this is the complexity. And the other one, so this is prims. The other one is Kruskal. It's m log m. So they're more or less the same thing. Okay, it's not really that different. Okay, so is this all very familiar to you, I hope? Any questions? I guess I'm just kind of in some way just reviewing for your final exam now in this course. Okay, so now I guess the question is, how do you apply it to real problems? And this is where I guess where I want to spend a bit of time talking about in terms of problems. So I chose 4 problems this week, and I will actually show you fractals first because I think fractals is maybe a little bit more straightforward. This is the most straightforward one. Okay, so there's a story, and so in an episode of Dick Van Dyke Show, little Richie connects the freckles on his dad's back to form a picture of the Liberty Bell. Alas, one of the freckles turned out to be a scar, so his Ripley's engagement falls through. I don't know if this is an actual episode, but anyway. Consider Dick's back to be a plane with freckles at various XY locations. Your job is to tell Richie how to connect the dots so as to minimize the amount of ink used. Richie connects the dots by drawing straight lines between pairs, possibly lifting the pen between lines. When Richie is done, there must be a sequence of connected lines from any freckle to any other freckle. Okay, so let's read this carefully. So there are a bunch of points, X and Y. So you have an XY plane, and you have a bunch of points. How many? Up to 1,000 points. Okay, so for each freckle, you have real numbers indicating XY coordinates. Coordinates have at most 100,000 in absolute value, so it can be negative. Okay, it's not really that important whether it's positive or negative. Okay, so there are a bunch of locations. You want to minimize the amount of ink used. Okay, so why do I say minimum spanning tree? Well, there's minimize. Ink. So ink would be basically the lines that you draw, the length of the lines. Richie connects the dots by drawing straight lines between pairs. So for example, like this, that's the line, and the amount of ink that I use is based on how long the line is. Shorter line use less ink. Okay, now this is another important thing. possibly lifting the pen between lines. So if I'm drawing like this and I draw like this, if I'm not allowed to lift my pen, then I must kind of go from here to somewhere else. I cannot do something like this. Okay? And then maybe this one goes this way and this one goes this way. Who knows? Okay, this is definitely not minimal, but this is one way to draw this. Then when he's done, there must be a sequence of connected lines from any freckle to any other freckle. So this just means that the resulting graph is connected. Okay, now as an aside, if I give you a graph and I tell you to draw it without lifting the pen, so no lifting the pen. Do you know how to do this? Do you know what this is called? I don't know if you've ever seen these brain teaser puzzles when you're a kid. It's like, can you draw these shapes without ever lifting your pen? So the standard, I think the standard one that people ask about is something like this one. You know, can you draw this one without ever lifting your pen? Have you seen this problem before?
I have.
Yep.
Yeah. So does anybody know what the solution is? Yes or no? And if so, if you can do it, how do you do it?
My best guess is it looks like a strongly connected component.
Okay, so you're thinking about strongly connected components. So strongly connected components, what does that mean? Do you remember what is the definition of a strongly connected component?
Can't you get to any other point from one point?
Between any U and V, there is a path from U to V.
I think those are
And-
directed though.
Ah, okay. I was going to say that. And another path, and this is important, another path from V to U, because this strongly connected components concept, it's a concept that's defined for directed graph. Yeah. So now, even if this is directed, even if I give you directions, that is still not the right approach, because strongly connected component just says that between any pair, you can go from one to the other and back, but it doesn't tell you that you have to use all the edges, right? Because I need to draw all the edges, and preferably only draw it once.
So would that be like a cycle?
It could be a cycle, but I mean, there's cycles here. There's a cycle here. There's a cycle all the way through. There are many cycles in this graph, but is that enough? Right? What if oops, let me change it back to my pen. What if you have something like this? That still have a lot of cycles. Can this one be done? This one, I think, can still be done. Anyway, I guess I'm not going to draw the standard picture, because then maybe that will give it away. So does anybody know the problem, the name of the problem in graph theory that covers this particular problem? Okay, I'll start with the first letter. This is kind of like a game that I play with my 6-year-old daughter now, trying to get her to tell me what the word is. Oh, hi, Alexander or Alex? This is a new person that just joined today.
Alex.
Alex? Okay, nice to meet
I don't
you.
really mind.
Okay, so we're kind of just starting to talk about this problem. Anyway, okay, so if you don't know what this word is, so that, as I said, I'm playing this game. If I was playing this game with my 6-year-old daughter, it would be like this.
We should play Hangman, Howard.
Well, apparently this is no longer allowed in school.
I believe that actually.
Apparently it's too violent, so they draw pigs. This is what I was told by my daughter. They draw pigs, and somehow the pig can keep on have more and more details. And the pig,
Interesting.
of course, never dies. Okay. So there are these words here. Okay, you want to buy a vowel?
A.
There's an A. Okay, I'll give you a good one.
Well, I think it has something to do with Oilers now, but like,
Uh-huh.
Well, I'm glad I'm not totally off.
Eulerian circuit. Actually, and I guess in this case, it's not necessarily circuit. It could be a path or path. Okay, so an Eulerian circuit or path. Circuit means, of course, you start from one place and end at the same place. And path means you start somewhere and you don't end up at the same place. But the important thing is Eulerian circuits and path means that when you go through the graph, you hit every single edge exactly once and no more, without ever kind of lifting your pencil. Okay, so you can have a path or a circuit that goes through the entire graph, hitting every edge exactly once, right? So in this case, okay, it's maybe, I don't know, how many of you know the general theory of when you can find an Eulerian path and when, or circuit, and when they don't exist? So Eulerian circuit exists if and only if the graph, first of all, is connected, because if it's not connected, you have no chance. And every vertex has even degree. Okay, and then if you want to talk about Eulerian path exists. So I'll use a different color here. An Eulerian path exists if it's connected and every vertex has even degree except 2 vertices. So 2 vertices have odd degrees, but everything else have even. So if you look at this graph, these 2 vertices have degree 3, and everything else, this has degree 4, degree 4, degree 2. So it satisfies this condition, so there's a way to do it. How do I do it? I start from one of the odd degrees, and I go to here, then I go to here. Basically, the even degrees kind of says that whenever I try to go into somewhere, I can always get out. I won't get stuck. And when I get stuck, it's because I have an odd degree. But as long as I get stuck at the end, then I guess it's fine. Here, it's the same thing. I can actually, this time there are 2 odd degree vertices. And if I start from here, if I don't screw up, then I can draw the whole thing. Anyway, so there are lots of applications of this problem. So for example, if you imagine that this is street map and you try to figure out is there a way that you can get your garbage pickup truck to go around the city without ever having to double back and all that stuff? That's essentially an Eulerian path, Eulerian cycle problem. Okay, back to this problem, right? So you have fractals, which are a bunch of x, y points on the plane, up to 1,000 of these things, and you want to figure out the best way to connect them so that the total sum of the ink that you use is minimized. So maybe you connect like this, and then you connect maybe this one, and maybe you connect this way and this way and this way, this way. Who knows? Maybe this is the best way. So what are we looking for? Right? Okay, maybe I don't have to tell you because we started talking about the problems of minimum spanning tree. So this is exactly a minimum spanning tree. Right? So this is the topic of today. So not surprised that we see a minimum spanning tree. But minimum spanning tree, this is the answer. I need an input graph. I need an input graph to compute a minimum spanning tree of. So what is my input graph?
Like an
so-
adjacency list?
Okay, so if I have a graph, I need to define, what do I need to define? I need to define the vertices and I need to define the edges, right? So what are the vertices?
There's a source and a destination.
Wait, what source and destination?
Oh, like you mean which for
What
The
vertices? Yeah,
the
what are the
scars
vertices in the
or
graph?
the freckles on him?
Okay, the
Yeah.
freckles, the coordinates that they give you, all these points. Okay, so every point they give you is a vertex. Okay, now what about the edges? What are the edges in this graph?
The ink between the freckles.
Which freckles? So how many edges are there? Perhaps I should ask you. And what are all the edges? Okay, is this an edge?
Yes.
Okay, it may or may not be an edge that you use in the minimum spanning tree. So if this is an edge, then the weight of the edge is the length of the line, right? Okay, so
Yeah.
the length of the line is the weight. Is this an edge? Okay,
Yep.
for those of you that have the camera on, I see you nodding. What about this one? What about
Yep.
this one?
Yep.
This one? Is there any
Yep.
line I'm going to draw that is not going to be an edge?
No.
So in other words, it's all u, v, where u is not equal to v. So all pairs of distinct edges, like distinct points, there's an edge between them, and the weight of the edge, of course, is the length of the edge. It's the length of that line, the distance between the 2 points. So this is actually a complete graph, right? Between every single pair of vertices, I have an edge. And the edge is simply, the cost of the edge is simply the length of the distance between the two. So with that, the code is actually relatively simple, if I can actually get to it. Okay, so it looks like I have a lot of code, but remember that this first part, all of this stuff is just direct copy and paste from my code library that computes minimum spanning tree. So in my code library, here's the minimum spanning tree code. I just copy and pasted it. There's no thinking there, because I recognize that this is a minimum spanning tree problem. I pull Kruskal's algorithm and then stick it in there. And then the real code is here. Okay, so I have to read in the number of cases. So they tell me how many cases I have. I read in number of cases. Then I loop through, let me make it bigger. I loop through that many cases. Okay, and then I read in the number of points. I read in the X and Y coordinates of these points. And then the indentation is a bit off in this editor, but this in the CADA submissions. But anyway, the idea is that for every pair of points, so this is a double loop that checks all the pairs of points, I add an edge where the two vertices are basically all the different pairs. And then the weight of the edge is just the distance between the 2 points, right? As you remember, if you have 2 points, xi, yi, and xj, yj, then that's yj. Then the distance between the two, it's xi minus xj square, so that's this thing, plus yi minus yj square, which is this thing, and then all square root, right? So that's pretty much all I do. I just set up this graph. So now I have a graph. the graph is just a list of edges. And then I call my MST code with the number of nodes, the number of edges. These other things are sort of parameters that are passed back by the MST code in case you actually, oh, sorry. This one is the list of edges. These two things are the parameters that the MST code passed back if you actually care about which edges you chose. Okay, and if you didn't care about which edges you chose, well, I basically have to pass them in and then you just ignore them. And the return value is the cost of the minimum spanning tree, which is exactly what I print. And that's it. There's some other thing going on that basically prints a blank line if necessary, but the main computation is really just set up the graph and then call the MST code, which is Cresco's algorithm. If you want to use Prim's algorithm, that's fine too. It's just that the version of the MST code in the library is Cresco's algorithm, so I just pasted it. Doesn't really matter which one you use. Does that make sense? Okay, so I'm going to backtrack a little bit because Alex is completely new here. So where are we? So in this site, there's a site called open.caddis.com, and there are lots of problems. Okay, so open.caddis.com, and there are lots of problems that have been used in previous programming contests. And it also allows, so there are lots of them. You can sort them by difficulty and try to do the easiest one first. So if I click on difficulty, and so they have some kind of scale. One point something is easy, and then the harder ones are much higher, 8 point something, 9 point something. And you can pick any problem. So for example, you click this one, and then there's some problem statement. It tells you what the input format looks like. It's kind of like an assignment problem. And that tells you what the output format is supposed to be. Gives you some test cases on this input. If you run your program on this input, your program's supposed to produce this output, etc. And if you think that you know how to do it, you actually wrote the program, let's say in C++, then you can click on submit your code, and it will tell you whether you got it right or not. And if you don't get it right, it won't really tell you why. It will just tell you you're wrong. What they do is they actually test your program on some hidden input that you don't see, and you don't get any part marks. Either you're completely right or you're completely wrong. If you get 99% of the cases right but wrong on one case, you are going to be told exactly the same verdict as somebody gets nothing right. So this is very strict, and there are lots of problems, and it also allows me to create a little contest that has a selection of problems, which is what I did this week. I selected 4 problems, and I created a little contest that has these 4 problems that all sits within one theme. Okay, so this is the problem that we just looked at, Fractals. Okay, so that's all I want to say about Fractals. Any questions? Anyone wants to stop me before I go on? Okay, so the next one, actually, I'm kind of moving not in the strict order. It's this thing called Arctic Network. So let's read the problem. So there's a Department of National Defense that it wishes to connect several northern outposts by a wireless network. 2 different communication technologies are to be used in establishing the network. Every outpost will have a radio transceiver, and some outposts will, in addition, have a satellite channel. Okay? Any 2 outposts with a satellite channel can communicate via the satellites regardless of their location. Okay, so it doesn't matter where they are, they can always talk to each other if they have satellite channel. Otherwise, 2 outposts can communicate by radio only if the distance between them does not exceed d, some number d, which depends on the power of the transceivers. Okay, so there's some d, that if you are within that distance, you can always talk to each other through a radio. But if you're past that D, the only way you can talk to each other if you want directly is to use the satellite. Okay, higher power yields higher D. So if you have higher power in your transceivers, it will allows you to communicate in further distance, but it will cost you more. Due to purchasing and maintenance considerations, the transceivers at outposts must be identical. So the value of D, it's going to be the same for every pair of outposts. So you don't have one place that have a stronger transceiver. Everybody has the same D. So your job is to determine the minimum D required for the transceivers. There must be at least one communication path, direct or indirect, between every pair of outposts. Okay, so the fact that it's talked about there must be at least one communication path between indirect or direct between every pair of outposts, that basically tells you that you have to make sure that everything is connected, okay, or the spanning part. But this is not exactly the same problem as the classic minimum spanning tree, because you don't really have a graph, I guess, and you don't really have this funny parameter D. Okay, so what else did they tell you? Maybe a little bit smaller so it fits in the screen. Okay, the first line of input contains n, which is the number of test cases. The first line of each test case contains s, which is up to 100. That's the number of satellite channels. And p, which is up to 500, the number of outposts. The number of satellite channels is less than p, it says. P lines follows, giving the xy coordinates of each outpost in kilometers, coordinates of between 0 and 10,000. For each case, output should consist of a single line giving the minimum D required to connect the network. Output should be specified to 2 decimal places. So here's an example. These are the points, and this is apparently the answer. Okay, so what is actually going on, right? So let's kind of draw this out a little bit. Okay, I meant to draw a square. You'll have to mentally undistort the square. So you have a point between 0, so x is 0, 100. So this is probably 0, 100. And then 0, 300 is somewhere up here. And then if I'm trying to do things according to scale, this won't work. But this is 0 to 0, 600. And then you have another point, which is 150, 750. Oh, shit. Okay, my square is definitely not a square anymore. So 150, 750 is kind of up here. Okay, so these are the 4 outposts that you have. You have 4. What is this? 4. 4 is the number of outposts, so 4 of them. And you have 2 satellite channels. So what does that mean? Satellite channels allows you to connect. Each satellite channel allows you to connect a pair, no matter where they are. Okay. So, for example, if you just decide to connect these 2, let's say this is the radius. This is 200, the distance. If you just decide to connect these 2, then it should take 200 to connect them. So if D is 200, then these 2 can be connected by radio. But these 2 cannot be. And these 2, I guess, cannot be, because this is basically 150 square plus 150 square root. So I guess it's something like square root of 2 times 150, which is 1.4 something. So what is it? It's a little bit bigger than that. Wait a minute, did I get something wrong? Y is the answer. So if I take the calculator, so how do I get a calculator?
Yeah, that's where the 212.13 comes from.
Yeah, okay, so that's what I thought, but why is the answer not 200? Okay, what am I forgetting here? Because I could connect these two. And then one of these can talk, maybe this one can talk to this one with a satellite, and this one can talk to this one with a satellite, the two satellite channels. Okay, so what is it that I'm forgetting? I'm forgetting something, because otherwise it doesn't make sense. Okay, let's just, what am I trying to do? Okay, so let's ignore this for now. We'll go to the code later to try to figure out why this is the case. Why the answer is 2112.13. Okay, so in general you have a bunch of points, okay, that you need to connect, and you have some satellite channels, S of them, that you can use. Now, if S is 0, if you have no satellite channels you can use, then the answer is just the standard minimum spanning tree, kind of. What do I mean? Okay, so you compute the minimum spanning tree, and that would, how should I, it's not a, okay, I shouldn't use the word minimum spanning tree. Let me try to. So you want to increase D a little bit at a time, increasing D a little bit at a time, I guess I could say. Okay, so, and then until everything is connected. Now, of course, if D, what is the smallest D you can have? The smallest D you can have is 0. So D is equal to 0, but that's not really interesting because you can't connect anything. So then you can try to increase a little bit. But what is a little bit? Well, if you look at, let's say if you look at the distance between all possible pairs, nothing will happen until you increase D to the shortest D. So that you go 0 all the way up to D0. So let's say you have all these distances and all the pairwise distances, and you kind of sort them in order. Okay. From 0 until you actually get to the shortest distance, nothing will happen. And as soon as you see D0, now you can connect this one. And then nothing, you can keep on increasing, nothing will happen until you get to the next smallest one. So maybe it's this one. Okay. And then until you get to maybe this next smallest one is this one. So what am I doing? I'm basically connecting the dots, provided that basically in the order of the edge weights, in increasing order. So what I'm really actually doing, it's Kruskal's algorithm, one step at a time. I'm sorting the edges and I'm connecting the edges, okay, from in increasing order. So maybe the next one is this edge. Maybe the next one is this edge. Maybe the next one is this edge. And maybe this one is, I don't know which one, maybe this edge. And then at some point, maybe this edge is connected. Now, Kruskals will not connect these edges because it creates zygos. We don't really care because we're not asking for the minimum spanning tree. Okay. And then maybe we connect this one. And then maybe we connect this one. Now, this is the first time, this is the very first time that the whole graph is connected. And the last edge that you choose, this one, is whatever this is, called DK. this is the largest chosen edge. And you know that if you don't use this edge, because this is the last edge that you use to connect everything, if you don't use this edge, you know that the graph will not be connected, right? So for sure you need this edge. And because you're considering these edges in increasing order, this is also going to be the smallest edge weight that you need, so that if you connect everything that is below this, less than or equal to this edge weight, you have a connected graph. But if you drop this any lower, you won't have a connected graph. And this is sometimes called a minimax spanning tree. I guess spanning subgraph, spanning graph, spanning tree, but it doesn't matter. It doesn't matter if it's a tree or not. So why is it called minimax? You take this subgraph and you take the maximum edge. This is the maximum edge in the whole graph that you chose, this whole subgraph, and you try to take the minimum. So you're trying to minimize the maximum. And that's why it's called minimax. And it turns out that basically you can use the same Kruskal's algorithm, and instead of just adding the edges that you chose along the way as the cost of the minimum spanning tree, you actually just take the maximum of the edge weights that you choose. And in fact, you don't even need to take the maximum, because you're going through in Kruskal's algorithm the edges in increasing weights. So the last edge that you choose is the maximum. And so the idea is that you sort the edges, sort all the edges, go through them in increasing order, and you keep connecting things until the whole graph is connected. And as soon as the whole graph is connected, you're done. And then the last edge that you chose to complete the connectedness of the graph, that's the answer, if S is equal to 0. So if there are no satellite channels. Does that make sense? Okay, I'm going to pause it before I go on. So what if you're allowed to use one satellite channel? Well, you can kind of do the same thing.
Howard,
Yes.
can I interject? I think the issue with the solution was that S doesn't count edges, it counts nodes, right? It's the stations that can connect to the satellite.
Ah, okay. So, okay, we'll come. Okay, so the problem was, okay, thank you. So here's the original graph of the problem one. So I'll kind of draw this on the side here. So two stations can have satellite channels, and they can talk to each other, and I guess they can actually talk to anybody. So anyway, I guess the idea is that you can choose, if you choose this one, that's 200, and then you choose this one, which is what was it? 212 or something like that. Then you can put you can put a satellite channel on one of these, doesn't matter which one, and one of these that will connect them. And then everybody can talk to each other directly or indirectly. Okay, that's probably what it was then. Okay, so the idea then is, if you have, so if you're allowed to use satellite channels, then what's going to happen? Well, what's going to happen is that you're allowed to actually have kind of connected components that are separate. So these are connected components. That means that inside here, any node can talk to any other node inside, and so on. But in order to connect these three, if you don't allow more radio channels, then you need to basically put a satellite channel somewhere here, a satellite channel somewhere here. Basically, you need to put a satellite channel somewhere within any connected component, within each connected component. and then they can talk to each other somehow to connect the thing. So if you're allowed to use S satellite channels, that means that you're allowed to have in your graph S different connected components. So if you allowed S equals to 2 satellite channels, you don't have to complete this edge. Okay, because you have 2 connected components, you can just use the satellite for this one. If you have more, then maybe you don't have to connect. You can stop a little bit early. So the satellite networks, the satellite channels allow you to stop the Kruskal's algorithm earlier than connecting everything. So what you have to do, it's basically you have to count how many connected components you have at every point. As you're running through the Kruskal's algorithm, you have to count how many connected components there are, and then when it matches up with the number of channels you have, then you're done. Does that make sense? So the next question, I guess maybe next or last question is, how do I know how many components I have? How many connected components I have currently while I'm running the Kruskal's algorithm? Do you know? So in Kruskal's algorithm, again, you have something like this for each edge. So I know that I have to say for each edge in increasing order of weight, but that's part of the Kruskal's algorithm to begin with. So I'm just going to write for each edge equals to UV. If UV not already connected, then connect U and V, right? That's basically Kruskal's algorithm with some other bookkeeping. So at the beginning, the number of connected components is exactly n. Every single node is by themselves. There are no connections. So the number of connected components is exactly n. Every time you connect, every time you draw an edge, what happens? The number of connected components decrease by 1. It doesn't matter how you connect them. You have some connected component that U belongs to. It could be just by itself, doesn't matter. You have some connected components that V belongs to, and you have other things too. Doesn't matter. These things don't matter in this step. And if they're not already connected, then you connect them. And by doing that, you decrease the number of connected components by 1, because these things now becomes 1 component. Of course, if they are already connected, then of course you don't want to connect them and decrease the count. So this is basically the standard Kruskal's. And then when the number of connected components is equals to the number of satellite channels, then you're done, right? With the exception of, I think you have to be a little bit worried about S equals to 1 and S equals to 0. You can't just say, wait until the number of connected components becomes 0. That's never going to happen. Okay, but if you have number of satellite channels being at least 2, then this is what you have to do. So where do I put this? If S is equals to number of connect components, then stop. And of course, provided that it's not one of these cases. Okay, so that's it's not exactly minimum spanning tree. It's this thing called minimax spanning subgraph or spanning tree, but it's a very common type of problem that's also can be solved in the same way. So another problem that's similar. So imagine that you have a roadmap. So you have a roadmap, you have cities or intersection or whatever, and you have roads, and the different highways and this way and that way or whatever. And you want to go from some place to some other place. Okay. Now these weights, there'll be edge weights, but the edge weights are a little bit funny. The edge weights are going to be the height of the tallest truck that you can go through. So for example, maybe you pass, there's some sort of bridges. So maybe this road, you cannot have something that's more than 6 feet tall, let's say. So maybe you know that it has to be anything to travel to this road has to be 6 feet or under. And maybe this road, there's less height restriction, maybe 10, but maybe this road is really restrictive. You better be under 4 feet. So you have to be driving a Formula One or something like that. And then the question is, I want to go from start to the destination using the tallest possible truck. Okay, because maybe that carries, that allows me to carry as much as possible. So how do I do that? Well, in this time, what you do is you go through edges in decreasing order. So you start from the biggest edges, and then you go with this from the biggest to the smallest, and basically sort of run Cresco until start and destinations are connected. And the first time that happens, the last edge that you chose is the shortest edge. It's sort of the shortest road that you must use to connect the two. And it's basically the same problem that, so this one is, I guess you can call it a max-min problem. So it's a minimax, you're trying to maximize the minimum. But it's essentially the same problem as before. You're trying to use the Cresco's algorithm to try to find the best way to connect the start and the end, where best means that you want a path so that the smallest edge on that path is maximized. Sorry, the smallest edge on that path is maximized. Okay, does that make sense? So if you follow all that, then I'm really going through these things in a very strange order, because I'm actually going to talk about the fourth problem now instead of the first problem. There's a lot of text here. So something about going through a vault to try to get coins, but anyway, it's easy. It's much easier if I just show you the sample input and tell you what this is about. So you have a grid, okay? So 7 by 5, 7 rows, 5 columns. Each of these numbers is a height. So imagine that this is kind of like a landscape, okay? At each spot, you can go up, down, left, and right. So you can go, perhaps I shouldn't use up and down. Let's say north, south, east, and west. Okay, because this is kind of three-dimensional. These are heights. If you move, okay, so if you go from, let's say here to here, and you climb up, then you have to bring a ladder. Okay, you have to bring a ladder. And this ladder better be at least height 3. Okay, because otherwise, if the ladder is shorter than 3, then you can't climb. If you were to go from 18 to 14, you don't really care. You just jump down. Apparently, it's safe to always jump down. So what you have to do is you have to try to go from the bottom. Wait, is it bottom left? Where is this now? So northwest to southeast. So northwest. So actually, it's bottom. It's start is actually the upper left corner. So you start from here, and you go to, this is the destination. So you go from the top left, go to the bottom right somehow. Every step you move in one of the 4 directions. And you want to bring the shortest ladder. Okay, so you don't want to use a ladder that is taller than necessary. So basically, you have a graph. You have a graph like this. You have these nodes, right? Like this. And then an edge that goes in all the directions, right? And so on. And the cost, if you're jumping down, so if you're jumping down, where am I jumping down in this? I guess, okay, so here, from 20 to 10, if you're jumping down, the cost is 0. If you're jumping up, if you're climbing up, the cost is how far you have to climb up. And you want to basically go from one spot to the next. So you want to find a path that goes from the top left to the bottom right, so that the maximum edge weight in that path is as small as possible. So you want a minimax path. Right? You want a path so that the maximum is as small as possible. So this is again very much like the problem we had, but there's now an extra twist. What is this extra twist? Why can't you just do exactly what I told you before with the previous problem? Yeah, build a graph, compute the minimax thing, and we're done. Why doesn't this work?
Is it because we'll have negative edges?
No, there are no negative edges, but if you go from 20 to 10, so if you fall down, the cost is 0.
Oh,
Yeah, so there's no cost. You don't really care what is the length of the ladder that you're using.
all right.
What is the difference between this graph that I'm drawing against any of the other graphs that we have seen?
The edges only go northwest, east or south.
Well, okay. That's
That you can't have diagonal, I guess.
well, okay, but okay, that's one difference, but there's a very big difference. There's a even bigger difference compared to the other graphs before.
And they're all adjacent. I don't know if that's
No.
what you're getting at, but
The edges that I draw looks like this.
oh, it's bidirectional. So it's
It's a directed graph.
oh, okay.
So before, when I connect two nodes, it doesn't really matter which way I connect them. But now this makes a big difference, because if I connect them one way, I might have to climb up. And if I connect it the other way, it's free. So I can't just connect edges freely. I have to be very mindful where I am and where I'm going to. So whatever we were doing before, none of them will work. But the good thing is, whatever we have been doing before are all variations of Kruskal's algorithm. We haven't actually tried to do Prim's algorithm. And it turns out that Prim's algorithm in this case will work. So why does Prim's algorithm work? Because in Prim's algorithm, let me just, I don't know if I want to show you the code or I just explain. Do I still have this page? Oops. Oh, I just crashed my, yeah, this whiteboard thing, unfortunately, it's, I don't know if it's a beta product or whatever. When it works, it's really good, but it seems like when I try to change pages, I have 50% chance of crashing the thing. Anyway, this is, I guess this is what happens when you are too cheap to buy a real product. Okay, what am I trying to do? Okay, Prim's algorithm. So what does Prim's algorithm do? You start somewhere, pick a starting node. Okay, pick a start node V. In this problem, the start node is the start node that they give you. Okay. And then remember that what you do is you say for every neighbor, for each neighbor U of V, add to a priority queue the following. The node U, I guess the node U, the priority value, it's equals to the weight of that edge. What is the weight of that edge? Well, the weight of the edge is the weight of going from V to U. What is that? Well, if the height of V, so if height of V is less than the height of U, that means you have to climb up, then the weight is HU minus HU minus HV. That's how far you have to climb up. If the height of V is bigger than or equal to U, then the weight is just 0 because you're jumping down or you're not really climbing. Okay. So then you do this, and then you have this standard loop while the priority queue is not empty. You say V equals to the front of the priority queue, and then you hop the front element, and then you do the same thing here. And then you add the edge from U to V. Well, from, I guess I would say, parent of V to V. So I guess in here, when you have to also add parents equals to V. So you know that you added U because of this edge from V to U. So you add this edge, and then you, again, for each neighbor, U of V, you do kind of the same thing here. Okay, so this is basically Prim's algorithm. And here, the fact that we are basically have a direction. We have to know where we're coming from. And in Prim's algorithm, you always start at V, then you start at your start node, I should say. Then you kind of figure out where else you can go. And then you incrementally build something based on where else you can go. And you always maintain the minimum spanning tree of what you have computed, all the nodes that you have seen so far. That's how Prim's algorithm works. Whereas Questco is a little bit funny in that you kind of connect things that might be completely far apart, and then eventually you kind of connect them together, right? So with Questco, it's hard to maintain the direction of where that you are starting from. It's hard to figure out where you're starting from and try to keep track of that because you're kind of all over the place. But if you're using Prims, you always start at the start of the graph, and then you incrementally add more and more vertices by connecting them to where you can go so far. So basically then, you keep doing this and you connect more things. And at some point, the destination will be added. So where do I put this? When the destination is equals to V, wait, where am I pointing? Sorry, I pointed to the wrong place. Here, when the destination is when the thing that you just pull out from the priority queue is in fact the destination, you're done. That means you have found a way to connect the start to the destination, and the max of the edge weight, the maximum edge weight in the tree, it's equals to basically the priority value of V that you just pull out from the queue. In other words, that's the last edge that you chose, right? The very last edge that you chose, that's the answer, because this is going to be the maximum edge of everything that you use here that connects you from start to the destination. So this is once again a minimax path problem. And once again, it's taking one of the classic minimum spanning tree algorithm. And instead of summing up the edges chosen, you take the maximum of all the edges chosen. And again, because we're using a priority queue, you're essentially looking at the edges in increasing order, so that basically the last edge that you chose, it's more or less the right answer. Is that true? Hang on. No, I'm being very stupid here. Okay, what I said, again, unfortunately I have this recorded. So anyway, what I said is completely wrong. You do have to compute the edge weight is not the priority. Okay, this is completely wrong. Cross it out. You have to have some kind of running answer, and then every time you pull something out, you have to say answer is equals to the max of answer and the priority queue of the priority of the entry that you just pull out, top of PQ. Okay, so why do I say that? So imagine that this is your tree, and maybe this is 5, and this is 3, and this is 7, and this is 10, and this is 1. Okay, it's possible that the last edge that you connect using Prim's algorithm is actually a very cheap edge, but because this edge is not discovered until you actually connect this node, along the way you have already used a long big number. Okay, so you actually have to keep track of that number a bit. Okay, hang on. Did I screw up again? What did I do or not do? Okay, why am I having trouble if I just did this problem? So why am I doubting myself? Because what if you have a really big number here, so a really big number here. So, and this may be the first, so you do this, okay, you connect this. Oh, but then if this is a really big number, you wouldn't have picked this one. You would have chosen this one first. Okay. So I think this is okay. So what was I worried about? What was I worried about was that maybe when you connect here, you need 10, but before you connect here, you see a bigger number. Yeah, okay, so hang on. Let me try to, yeah, no, it cannot happen. Okay, so I think I'm safe here. So let's just quickly look at my code just to make sure that I didn't screw up what I tell you. So I have the height that I read in. So I read in MNN, the size of the grid. I read in the height. Okay, so these are heights. And then I have some answer, which is the height. So for each node, I remember what is the best height I can, that I get there. So for each node, if I go to that node, what is the minimax height that I need to get to that node? I have a priority queue. I have to store 3 things. I store where I and j is where I go to, and d is this minimax distance. So, okay, so I did it in a little bit differently than what I wrote, but basically I just pushed the start, and then while the queue is not empty, I pick the thing off the top. So this, I don't know how many of you know about this stuff, but I use in STL something called tuple, which allows you to group any number of things as long as a fixed number of items into a structure. So it's basically a pair, except that I can use triples, quadruples, and whatever. So this basically three things. And when I do emplace, basically that construct a new tuple with three things and stick it into the priority queue. And then this is a way for me to take the thing out. So pq.top takes the tuple out. And this tie function allows me to assign the three things in my tuple into three different variables. So it kind of allows me to pick it apart. That gets rid of the front of the priority queue. And then, oh yeah, okay, I play another trick here. So I played a trick that my distances, I always put the negative of the cost into the priority queue, because the standard C++ priority queue sort things by giving you the maximum. So it always gives you the maximum item in the queue. But I don't want a minimum, so I kept the trick that I played was I negate everything. So instead of storing the actual cost, I store the negation of the cost, and then pick, when I multiply by -1, then largest becomes the smallest. So that's kind of the trick that I play. And this basically says, if I have seen it before, or if the distance that I find it's actually worse than what I found before, then I ignore it. Otherwise, I look at the neighbors, and this is just a way for me. I2 and J2 are basically the neighbors. I do some funny things to look at the 4 neighbors and make sure I didn't run out of bounds. And then the cost here is basically either you try to climb up, but if it's negative, then I set it to 0. So if you try to fall down, then the cost is 0. And then I also make sure that, what do I do? If I can already get here somehow with a longer ladder, then I will actually just keep that. So anyway, then basically this just makes sure that if I haven't seen it before, and then I push it into the queue. So this is kind of like the Prim's algorithm. And if you remember correctly, actually, for those of you that did the regional problem, you have this problem called conquest. You remember that there's a graph of islands, and the army can try to conquer other armies, other nations, and you can basically conquer somebody if your army size is bigger than the other island, and as you conquer them, you kind of assimilate the army and grow your army bigger and bigger. And your question is, how far can you conquest? How many other places can you conquest? And it's almost exactly the same algorithm. Okay, okay. The last one is actually maybe the most straightforward one, and it comes to the minimum spanning tree, but maybe it's a little bit hard to see why it's a minimum spanning tree. So the backstory is that you're doing cat sitting, and you have to feed cats. Okay, you have to feed cats with milk. Your ant, it has 3 complications. Your ant has a limited amount of milk. For each pair of cats, there's a distance that you have to keep them apart to avoid infighting. And because you don't like cats, I guess, so you end up drinking a lot of hot liquor. So you cannot move liquids without constant spilling. In fact, you will spill 1 milliliter of milk you carry every meter you walk. Okay, so given an amount of milk and a set of cats, each pair of cats being given the distance apart from each other, so they'll tell you how far apart each pair of cats are. Determine if it's possible to feed every cat at least 1 milliliter of milk. Every cat has a cat bowl that can hold an arbitrary amount of milk. For every meter that you walk, you will definitely spill 1 milliliter, instantly spoiling it. But instead of carrying all the milk at once, you may serve a cat more milk than needed and pick it up when backtracking. The cat will not drink the excess milk before you finish walking. The cats will never move, but they will eye each other with intense hate. Okay, so you're given T cases, which is up to 20. Number of cats is up to 20,000. No, sorry. Number of cats is up to 2,000. M is the number of milliliters of milk that you have to start with. And then you have this distance matrix where they tell you the distances between the cats. So for example, here, between cat 0 and cat 1, the distance is 4. Between cat 0 and cat 2, the distance is 3, and so on. They will tell, this is a complete graph. They will tell you all the edges. Okay, so what are all these things that they tell you? Okay, so there's a graph, that's clear. There's some kind of a graph. You have to walk and give milk to everybody, but when you walk, you will lose milk. Every time you walk a meter, you will lose milk. You definitely still, but instead of carrying all the milk at once, you may serve a cat more milk than needed and pick it up when backtracking. This is kind of important. So imagine that you have 3 cats like this, and you want to go from this cat to this cat. I don't know, distance is 5, and this cat is, let's say distance is 7. You want to go from here to here, and then, okay, I think I need one more cat to make this work. Let's say this is 6. You want to go from here to here, and then here to here, and then you have to backtrack, and then you go here, let's say. Because maybe that this distance is really large. Maybe this distance is 100. So it's actually better to backtrack and go. Okay, so now how much milk do you have to take? Well, obviously, if you want to feed this cat, you need at least 1 milliliter. So right off the bat, you need to have 1 milliliter. When you walk this way, you're going to lose 6. You're going to lose 5. You have no choice. When you walk this way, you're going to lose 7. So you're going to lose 12 for now. Of course, this cat needs 1, and this cat needs 1. Every cat needs at least 1. So actually, the number of milliliters for each cat is exactly C. If you have 4 cats, you need 4 milliliters to feed them as a minimum. So you go here, you go down here, but now you walk back. So then you might say, well, I need to lose another 7. And then you walk this way, you lose another 6. Okay, maybe I should write this as 5 and 7 instead of just 12. Now, there's one very important thing. Instead of carrying all the milk at once, you may serve a cat more milk than needed and pick it up when backtracking. So whatever amount of milk that you're carrying, you can drop almost everything here. When you first come here, you just drop it all here, except that you need 8 milliliters because you're going to go here, lose the 7 and feed the 1. And it's okay that when you backtrack, you're empty-handed. In fact, that's better because when you're empty-handed, you can't lose milk. And then you can pick that up and keep going to deliver this one. So this 7, actually, you don't have to lose this 7 twice. You only have to lose the 7 once. So if this is the path that you're going to take, go from here to here, then backtrack and here, then the amount of milk that you're going to lose, it's going to be 12, it's going to be 18. And the amount of milk that you must feed to each cat is 4. So as long as you started with at least 22 milliliter, then you can do it. If you started with less than 22, you cannot do it. So now again, the number of milliliters you have to feed to the cats, that's fixed. You have to feed at least 1 milliliter to each cat. You have the fixed number of cats, so this part is well known. You also know that you started with m milliliters. So what we know is that this quantity is the maximum amount you can lose while walking. You cannot lose more than this. So what is the minimum amount of milk that you can lose? Well, basically, because you're allowed to backtrack. When you backtrack, you don't have to, as long as you plan carefully, when you backtrack, you don't actually lose anything. We're just looking for the cheapest way to connect them. Because as long as it's connected, you can walk back and forth between them, and backtracking never counts. You only have to remember the first time that you walk that edge. So the cheapest way is the sum of the edges. In other words, it's a minimum spanning tree. If you don't have this, if you're not allowed to drop things at a place and pick it up later, if you must carry it all the way through, then you are basically looking for something very different. Okay, what is something very different? You're trying to find the best way to visit all the nodes, right? You're trying to find the best way to visit all the nodes at least once. So if you are not allowed to drop things and pick it up later, then you're trying to find the cheapest way to visit all nodes at least once. Now, it turns out that this is slightly, but not too much, slightly harder than the problem of visiting all nodes exactly once. Okay, it turns out that it's not that much harder, but if you want to solve this problem of at least once, you have to be able to solve exactly once. And does anybody know what is this problem called? The cheapest way to visit all the nodes exactly once in a graph. Has anybody heard of this problem? Okay, do we do the hangman again? Okay, I gave you one of the words. Does anybody know what the next word is?
Salesman.
Traveling salesman problem. Given a particular graph, try to find a way to visit all the nodes exactly once, and you want to do it in the cheapest way possible. And this problem, it's what we call NP hard or NP complete problems. And basically it means it's really hard. If you take 3200, you'll discover that if you have n nodes, you can solve this problem in 2 to the n times n squared time operations. So 2 to the n, of course, grows really quickly. So if n is bigger than 20, you're basically toast. Okay, and in this case, n was, the number of cats was what? 2000. So 2 to the 2000, you're toast. No way. Okay. And I mean, there may be faster algorithms, but nobody knows how to do it in polynomial time at this stage. So if you don't have this constraint that says you're allowed to drop your stuff off and pick it up later, you must carry it all the way through, you are really in trouble. There's no good way of solving it as far as we know. So if you recognize, once you recognize that this is minimum spanning tree, well, the code is really not that hard. I mean, obviously there's a lot of code, the same code that I pasted about minimum spanning tree. Okay, there's not much to see here. It's the same code. And then the solve is really easy. You read in the number, you read in M, you read the number of cats, you read in all the edges, call the minimum spanning tree algorithm, and if the cost of the minimum spanning tree plus the cost plus the number of cats, if that is no more than the number of milliliters of milk that you started with, you say yes, otherwise you say no. And that's it. So if you already have the code for minimum spanning tree, this is really easy. You just have to recognize, once you recognize this minimum spanning tree problem, then you just have to set up the input and then you just call the function. So I think one of the things that I want to say is if you have a graph problem, especially if you recognize that this is one of those standard algorithms that you learn, and of course, if you already have the code library, then really the main battle is, can you get your input into the form that it's required by the algorithm? And once you call the algorithm, can you then take the output from the algorithm and interpret it in a way that it's required by your problem? And most of the time, so I shouldn't say, at the level of, let's say, the regional contest and below, most of the time, they are not going to ask you to invent a graph algorithm for a problem that's non-standard. So everything is going to be some kind of variation of standard problem that you see in an algorithms class, possibly maybe in the fourth year algorithms class instead of just the first one. But chances are you are going to pick one of the standard graph algorithms, and then you just have to massage your input so that it looks like the right problem, and then you massage the output so that it gives you something useful for the answer. Even at the World Finals library, even at the World Finals level, I would say most of the graph problems are still in this kind of category, except that they might sometimes require you to use 2 or 3 different graph algorithms together in a way that maybe is unexpected. But most of the time, it's still relatively standard graph algorithms. So when the kind of graph algorithms that you learn in 3620 and other courses, they're going to show up all over the place. And well, it's just not, I guess it's not just programming contest problems, of course, it's in real life too. So there's a reason why we actually teach you this stuff. I guess this is what I'm trying to tell you. Okay, so that's it, I guess, for this week. As usual, if you go to my GitHub repository, you'll see all this code. So you can just go and look at it if you want. Now, I guess you people are going to be busy with exams and such in the next little while. So normally I run something in the summer. I have no idea what everybody's doing this summer. So let me maybe stop the